The senses words together.
Hey Adam, what room are we in?
BSC 4, no, 141.
141?
You periscoping right now?
I am going, we're live. We're live.
Who's watching? Why? Who watches these live streams?
Very, very positive approach. Thank you.
No, I'm just like everyone who would watch it is here.
No, there's two people. There's one person.
It's going to be 3 now.
Is it like
here?
We're starting in a couple of minutes. Be patient. Emma, stop. You know this is recording, right?
You know it's live. It's strange.
Well, should I? No, maybe. Okay, hang on.
Whoa! It's okay, man. I don't want to miss the presentation. We're in sideways. You gotta sit back. Turn.
No, but that's not. What if you turn your phone though?
It reorients.
Okay, now it's right.
Sideways.
What?
Yeah, this is.
This is not exactly how I'd anticipated this starting. I'm sorry about that. But here we go. This talk is called In the Name of Performance. I'll explain what that means in a second. I'm Sam Coleman. Who am I? I graduated in May of 2015. I graduated from CS program. And since then, I've been working for a company called RBR, which makes very expensive underwater thermometers. This is not a pitch for a company. This is just proof that as an Acadia graduate, you can get a job. What is this presentation about? Let's start by talking what this isn't about. This is not going to be about how to architect your overall solution. There are lots of great books on that. One of these books is Release It, which is about as a system as a whole, not just code. How do you design your system to work with your deployed environment? How do you think about external stuff like the servers it's going to be running on, and stuff like deploying the database it's going to be talking to, and architecture of load balancers and all these things. It's a little bit out of date in today's containerized world, but it's still worth reading. And Clean Code and Code Complete are two both very good books on overall how do you structure your code. That's not what this is about. This isn't about how to walk into a really crappy code base and sort it out head to tail. This isn't about taking ownership, refactoring large scale, and fixing things. This is about gross things. This is about an atomic unit of code. This is looking at one function. This is looking at one small block of code going, hey, this is really awful, and I can't even read it. How do we look at this? How do we start approaching something that we don't even understand? We can see that numbers go in and numbers come out, and maybe based on the name of the function, hopefully based on the name of function, we'll have some idea of what it's supposed to do, but we don't know how it does it. And until we know how it does it, we can't change it. We can't replace it with something that reads better, we can't comment it better, we can't make a good call as to whether it needs to be there or not. The reason this talk is called In the Name of Performance is because, as it turns out, most of the reasons these sorts of blocks of code are in existence in the first place is because somebody at one point said, this is faster. This is the fast way to do this. This is going to save us microseconds. I made a mistake on my title slide. The subtitle for this talk should be C is not your mother. Because as it turns out, both of the code examples we're working in are in C, and C is one language that makes it very easy to make these sorts of terrible decisions, or find yourselves in these sorts of pitfalls. The first thing I want to look at is something called Duff's device. Some of you may have seen this. I don't know. Wow. Okay. Duff's device is one of the most famous examples of a really crappy piece of code. And what I want to do is I want to build it with you guys. I want to start it, what it's for, what it does, and then transmogrify a very simple piece of code into the final result to give you some idea of how these sorts of awful contraptions end up in a code base in the first place. Duff's device comes from a simpler time where copying bytes from one memory address to another was considered to be a big freaking deal. The idea being you have a block of n bytes that needs to end up somewhere else, and it's a very simple copy operation. In C, well, it looks something like this. I have a function that's going to copy from one place to another. I have a destination pointer that I want to put things into. I have a source pointer that I want to take things from, and I have some number of bytes that I want to take. So, we're going to start at the 0th byte. We're going to walk along for all of those bytes. And at each point, we're going to copy into our destination the value at the source. After we've done the copy, we're going to move our destination pointer along, and after we've done the read, we're going to move our source pointer along. And because we were given these as void pointers, we need to cast them to an actual byte value we can work with, so we'll just do and as with any live coding example, this is going to be full of compiler errors the first time I try to run it, and everything's going to break horribly. So if you see me making something really obvious, just yell it out because it's going to save us all time. But so there's your basic concept. We've got some source and a destination, and we're going to copy from one to the other. In order to verify that what I've done here isn't insane, I took the liberty of, and here's where the guy on the infomercial brings out the pie that he baked up perfectly ahead of time. I have a test, just a basic test runner. I defined some input data and a similarly sized array that we're going to copy to. I run my copy function, which I've defined over here, and then I check to see whether the copy was correct or not. Okay, great. Let's compile and run this. I'm going to make loop. And now I can run that. Oh boy. Can anybody see why this isn't printing correctly? Because I can't. This is not actually supposed to be part of the presentation. Oh, there we go. Okay, so it's only going to print out the 2 results. That's still a little shady, but we'll live with it for now. So that does what it's supposed to. So here's where Duff's device comes in. Some guy whose name was presumably Duff decided in the good old days of poorly or non-optimizing compilers and slow machines that this is not a great way to go about copying bytes. Every time we copy, we run through this for loop. Those of you who've taken architecture know what a branch instruction is. For those of you who don't, it's a CPU level atomic unit of thing that the CPU can do that says, is this the case? Let's do this. So that means for every copy, we're also performing a branch. That's super inefficient. That means you have, in terms of CPU instructions, not necessarily clock cycles, but in terms of instructions, you have a 50% overhead on this copy. So this is where something called loop unrolling comes in. If I have something that I know needs to be done the same way multiple times in a row, I can just do those things, and I can set up my for loop or my overall control system to break out as appropriate, but just let me run the thing. So we can copy this line, 2, 3, 4, 5, 6, 7, 8, and we can limit our loop to increment by 8 every time with a little check to make sure we don't go overboard on the copy. And we can do our copy. So now we have a much better overhead because we're only performing 1 check for every 8 copies. So let's see what that does. My printf still isn't working, and I would still love some feedback on why it's not working. I swear this was working last night, so I've either screwed up something significantly or... no, so we call copy to copy from A into B the size of A. That's what should be happening. And clearly we're getting, clearly mem compare was happy with our result before.
In your copy function, did you have the destination first?
Yeah, universal parameter. You're coming from,
No, because I should be setting into my destination.
yeah, but calling parameters reverse.
So you're saying if I did something like,
No, not
Just
just
at the
back
top,
to
you
the main.
change void S into void source. Switch those two.
oh,
Yeah,
darn.
Copy B8.
Well, I'm an utter nincompoop. There we go. Okay. Now, the problem seems to be that we haven't actually copied all of our array. The problem being now that our loop only copies in multiples of 8. We only copy 8 bytes. We need some way of taking care of that overflow. So what we can do, first we'll lift out our size so we know how many we had left when we're done, and we can set up another loop. And this will be just the way it was originally. While we have leftover bytes still, we'll keep finishing off the copy. And now if we run that, great. So that works the way it was supposed to. Everyone's clear about this? It makes sense. So we do our blocks of 8, and then we finish up. The downside is that we still have a finish upset that is discrete from our main loop. It would be really nice if we could condense these into one thing because it makes the code shorter. It doesn't, in this case, make the code more readable. We don't care about code readability. Remember, we're the guys in the 70s who care about performance, and that's all. The first thing we can do we also want to get rid of, our ultimate goal is to get rid of as many branches as we possibly can. So where we can start in consolidating these is by getting rid of this loop as a loop. If we know we have this many bytes left over, we can say if our leftover is 7 bytes, we will never have more than 7 bytes left over because if it was 8 or more, this would have taken off another chunk. So if it's 7, we can do 1, 2, 3, 4. I'm not going to do it, but you get the idea. If we have 6 left over, we can do 6 of those. This is going to get real tedious real fast. Those of you who have a little bit of maybe done some compilers or maybe tried to do a parser, you might have run into the switch statement. And a switch will say, a lot of people consider it to be sort of a slimmed down if, but we can say if we have 7 left over, do you copy? If you have 6 left over, do you copy? If you have 5 left over, do you copy? Because how the switch works is that the switch will evaluate whatever value you pass in and then jump to the appropriate case. When you write a switch, you will normally end up with a break after this, right? You've used a switch. You know that you write your case, you do your code, you have a break. The reason you have the break there is because switches are a little tricky. If you don't have the break there, the program will keep running at the next operation. It'll just happily skip over this label and keep running through the rest of the switch. So if we do, how many more? I think I need one more after that. 3, 2, 1. No, I got them all. So if we have 7 left over, it'll start here and then run this, and this. If we only have 1 byte left over when we enter our switch, it'll enter at the 1, do it, and leave. So that's it. We're done. We don't need that anymore. And we can just confirm that it's correct. Great. So now we really only have 1 branch instruction for the end because you've probably all been told at some point or another to never use goto. At a fundamental level, when you're writing assembly, jumps compile down to go-to. So even if you don't want to use or don't get to use a go-to, the compiler still does. And that's what switches become at an assembly level. And I don't have time to tear this down into the assembly. I'm sorry, I was going to try and it didn't really work out, to show you what the compiler generates for this. But this switch will become a go-to. And it'll go to 7 or 5 or 3 or 1 as appropriate. The trick is that, as we've already discovered, switches don't really care about anything other than jumping in at a point and then just running until it hits a break or until it hits the end of the switch. So we can start to do some really hideous stuff inside a switch. If we were to, say, put a loop inside the switch, this would keep running infinitely. Well, it won't if I don't have the brace, but if I have the brace where it's supposed to be, then yes, it will keep running infinitely. So, tip for anyone doing presentations, remember to purchase your software legally before you run the presentation with the software. You can probably see where I'm going with this. If we have 0 bytes left over, we could do that at the beginning, and we jump in and we copy a full 8 bytes, which means we can just drop all of this, keep our total number of increments out. Once we get to the end of our loop, we can punch up our counter, and we can keep going while I is less than n. And unless I've done something wrong, oh, no, I have done something wrong here. 0, switch on our leftover, yep. So our leftover, if we haven't copied anything coming into the loop, is going to be how many bytes are left over if you take the size of it divided by the remainder by 8, and you want to round that up. No, you don't want to round that up yet, sorry. That's just going to be our leftover. So that's if we have 33 bytes, that's 1 more than 8, so we're going to have 1 byte left over. We're going to start on 1, and then we're going to keep wrapping around again. We also need to increment by 1 for every pass, every time we copy. We'll get rid of that in a second though. This can get done, so don't worry. So if we run that now, okay, it does what it's supposed to do. Congratulations, we can throw out this loop. Who needs loops? We don't need loops. You might notice that we also have this increment operation every time. It would be really nice if we could get rid of that. So now we've eliminated most of our branching overhead, but we still have this finicky increment that we don't need when we've already got these others. So what if instead of counting the number of bytes copied, what if we counted the number of blocks which we needed to copy? So our number of blocks is going to be the number of segments you can make of the total number of bytes being copied divided by 8, and that's where you need to round up, so that if you have 33 bytes, you can't just do it in 4 passes, you need to do 5. Okay, fine. Once you get to the end of your switch, and I'll try to keep all of the code in screen here. Sorry, I'm scrolling up and down like a maniac. This is probably pretty hard to follow. If we increment blocks, and if that result is greater than 0, we'll just keep going. Oh dear, it works. Why does this work? Who let this work? This is hideous. Just to make things worse, it turns out the only place we use leftovers is in the switch, and you can evaluate an expression in the switch, so you can do that. And I'm not sure if you've ever looked at any C code, but in most cases, people actually align the case with the switch because it really is a label, not a line of code. So that means that you can reformat this as something a little bit more like this. And 3, 2, 1. And it copies successfully. So that's how our grandfathers from the 70s still come back to haunt us. That's what's called Duff's device. And now you know how it works. and now you know to be afraid of it. Don't do this. This is awful. Clearly, as you can see by the reactions of those around you in the room, this is not obvious. This is not something you think of doing in your daily lives. And the fact you don't think of doing it in your daily lives is a credit to all of you. The point in this is to note that C, even when you think you know it, and not just C, but any language, even when you think you know it, there's still darker corners. Somebody showed me something like this in Java the other day. Why would you do that? This does work. In C, this is undefined behavior. In Java, this is perfectly valid, and it does work the way it's supposed to. N is prefix incremented, so this operation returns the new value of n, and then you're just setting n to the new value of n. It's fine. It does what it looks like it does. But why would you do that? And you will find code that's like this. The other reason that you shouldn't do this is because memcopy is available almost everywhere. And if you look at the documentation in glibc for the memcopy function, it very explicitly says memcopy will have performance of no worse than Duff's device, which means if you have memcopy available to you, you don't need to do this because somebody else already did it. The reasons you would still consider, or the reasons you still might find Duff's device in a program is largely limited to embedded systems where you might not have a full standard library. You might have the very most Spartan C compiler you can possibly imagine and nothing else beyond that. And if that is the case, I'm very sorry for you. Relegate this to the deepest, darkest corner of your code base. Comment it well. There's no reason for this to look like this. You can add, yes, Virginia. How do you spell Virginia? There you go. Demons do exist and this loop does execute. That's not a good comment, but you can see my point. You can explain this stuff. And if you do have to encounter this, once you've torn it apart, comment it. It's going to make life better for everyone. That's sort of the first half, and if everyone wants to stand up and leave, that's fine. You're welcome to it. We'll take a 30-second break for you to do so. The second question comes courtesy of Tyler Jodry, who ran into this question in, I guess it was in an interview.
Yeah.
The question was, given a 32-bit integer, which bits are set? Which bits are on in this number? So and this question can be adapted for a char value or for a 64-bit int or whatever you want, but you need to count the number of bits in an integer. Before we get into the meat of this, I want to make sure everyone's familiar with the bitwise operators in C for and right shift. So if I have an integer and I have another integer, then anding them is just performing a binary and on every bit column in those numbers. A right shift is taking all of the bits in a number and moving them one bit to the right. Any bits that fall off of the right edge will be discarded, and any bits on the left side will be filled in with zeros. So that's what a right shift is, just to remind you. Masking, which is probably a word I'm going to use a bunch of times without even really realizing it, is a word for having some constant value, something like 0011111100, that has some meaning to it. And when you AND that mask with your input value, your result will be the value of the input wherever the mask was 1, or 0 wherever the mask was 0. So it's a way of selectively isolating just some bits of your input. That's why it's called a mask. It's a bit like a stencil, really, but stencils mean something else in computer graphics, and for whatever reason, the term mask caught on, so that's fine. I need my other set of files. I need this one, and this one, this one, and this one. Don't look at that yet. Let's think about how we do this in our most obvious fashion if we wanted to do this. Well, we're going to have some number of bits that are set that we're going to want to return. So this isn't terribly useful because right now it says every number has 0 bits set. I don't think that's correct. So I guess we have to iterate somehow over every bit in the number, so we'll set up our loop. And we've got a constant here even to tell me how many bits are in a number, so let's do that. Okay, so one thing we can do, which we know how to do because we know what masking is, we can isolate the rightmost bit of a number, the least significant bit. We can do that by saying value and 1, because the binary value of 1 is, as it turns out, 1. This expression will return either a 1 or a 0 based on whether the rightmost bit is on or off. So we can just add that to the value of our counter. Fair enough. Once we're done that, we also want to shift value over to the right by 1, so that when we run through this loop the next time, we're looking at the second bit, and then the third bit, and so forth, even if they're still the rightmost bit in our value, but as far as the total input is concerned, they're the next bit. So I'll just simplify that into a shift and equals operator. Let's test this. My main program is a little bit more complicated here, but I'm just going to gloss over it because when it runs, it's a little more obvious what it's doing under the hood. All I'm doing is generating some test cases and then running each one of those test cases through my bit count function and seeing what the result is. And if I run shift, okay, so that's logical. These are the hexadecimal representations of the inputs into the program. My loop just set it up so it sets a bit in every position, and then it progressively sets all the bits in the number. And in all cases, it passes. So that's fine. My bit shift works the way I expect it to. I can close the main now because I'm not going to be using it anymore. Let's think about how long this takes to run. This takes 32 passes of this loop because there are 32 bits in the integer, and for each one we perform some operations. So it does run in constant time. For those of you who care about algorithm analysis, it's a fixed amount of time. This isn't going to run slower or faster for different sorts of numbers. Every time it's going to evaluate all 32 integers. That's fine. But maybe we can do better. So maybe we pull open Stack Overflow and we find this. Can anyone tell me what this does? Because Stack Overflow says it tells me the numbers of bits set in a number. So I see gobbledygook, but unfortunately, let's say I was not facing this on Stack Overflow, where I could selectively elect to say, no, that's stupid, I don't care what it does, it's hideous, I'm not putting it in my code base, I'm just going to do the slower thing. And let's say I'd found this in the deepest, darkest corner of a program that I'd been handed, that had been put on my desk and said, make this work with 64-bit integers with bit counting, and I don't want you to do it the slow way. So, where do we start? The very first thing I would do would be to try to isolate at the lowest level, what is the smallest piece of this that I can break off and start figuring out what it does? Well, the first thing that stands out to me is these hexadecimal constants. I don't like those because I don't know what they're supposed to mean. I know what a bit mask is. You all know what a bit mask is. We just went over it. Clearly, these are bit masks because they're being ANDed with the input values, but we don't know what they represent because they're in hex. Java 7 implemented a literal type for representing binary values, which looks a little bit like 0b instead of 0x, followed by a series of 1s and 0s. That's nice, but we're not in Java, we're in C. Turns out that the GCC implements an extension for that same sort of literal representation of binary numbers. If you compile your code with all warnings as errors and all warnings enabled, you do have to explicitly enable that function or else it'll throw an error at you. That's fine, we can convert these back to hex later and just compile with that enabled for now. For now, we just want to see what these are. So my makefile is already set up. When I try to do this, it'll work. So all we're left with is figuring out what are these. This is a little bit of a sidestep, but for working with binary numbers, the BC compiler is incredibly useful. You can tell it what base to work in for its output. We want base 2 output, and we can tell it that our input should be in base 16. And then we just pass it in a number, and it tells us what it was. Turns out that the hexadecimal 5555, etc., is just every second bit set on, starting with the least significant bit. So let's define a constant for this. I'm going to call it bit alternating, because that, type what I tell you, because that's what it seems to be. And I'm going to cheat here because I've already looked at this, but I'm just going to align it to 32-bit values, because then we can see our whole 32 bits in a row. And now we can sub this in where it's used. And then we can do the same for all the other binary constants. So this to me looks like alternating pairs of on and off. And let's pad that out to 32 bits as well. That is, let's call them quads of bits on and off. And lastly, we have this, which even just looking at it, it's 1, 0. So each pair of hex values is equivalent to 8 bits, and if it's just 1, then this must be the first of every byte flagged on. But let's just confirm, yes, this is every least significant bit of every byte. So let's call this yeah, sure. Okay, clear as mud. The next thing we can do is try to see if there's any pattern to these. One thing that stands out is that there's typically a value with some shifting and some masking, and a little bit of arithmetic. So we've got some masking and arithmetic and shifting, and then we've got arithmetic and shifting and masking, which doesn't seem like the rest of this line. So I'm going to take this sub-expression out. And because we have a test program, we can confirm that to this point, we haven't broken any of its behavior. So before we go any further, let's do that now. Okay. Okay, so everything's still fine. We're still passing everything. Now let's start to try to peel apart what this does. Well, we can still line it up a little better. We can line up our arithmetic operations, and we can line up our shifts. So really now is where the meat of what does this do comes into play. At this point, I would start trying to feed some values in. One thing that I find useful when you're trying to decipher bit operations is don't feed in a string of 1s and 0s, because your masks are going to be 1s and 0s, and you're going to want to try to figure out how your masks and your shifts are affecting the input. So feed in a bunch of letters, running right to left, try to visualize the operations on a piece of paper, and write down A, B, C, D, E, and run that through. I did that, and in the sake of time, I'm just going to, oh darn. Let's see if I can get PowerPoint to work, because I have some animations on this slide. And when I tried this before, it was a little bit flaky. When I went full screen, it changed my screen resolution. We might have to just live with it.
Or not.
Okay, so if we write down, on our first operation, we had the input plus the input shifted over by 1 bit, and then masked some. So if we write down what it's doing, we've got our first line of input, and then we've got the same input again, shifted over by 1, and subtracted from the first one, and we have a mask that kills off, replaces with 0. Every second letter, or every second symbol in the shifted input. If you sit and stare at that, you might notice that there are some trends in there. There are some vertical sort of commonalities. It looks like it's doing the same thing over and over and over. So this is a good point to, and maybe this works for you and maybe this doesn't. It turns out in this case this worked, so I didn't have to explore the alternatives. But if you take out just one chunk, remember our goal here is to break this down into the smallest component that's doing something and work backwards from there. So it looks like in this case, the smallest component that's doing something is one set of 2 bits. You're at the smallest point here. You can start replacing the letters with real numbers and see what it does. And it turns out that if you feed in some 1s and some 0s, the left column always stays as whatever the left column was, and the right column ends up being the XOR of the top and the bottom numbers. That is to say, it's on if C is on, or if D is on, but not both. Which means the possible output of this 2-bit 2-bit arithmetic operation is 1001 or 00. That is to say, 2, 1, or 0. So all that this really complicated expression does is figure out for each 2-bit pairs how many bits were set in that pair. That's not the slide I wanted it to be. So we end up with every pair of integers in this result, or sorry, every pair of bits in this result, saying for that pair in the input, did this pair of numbers have 1 number set, 2 number set, or 0 number set? So we can kind of hypothesize that that's all that the rest of this is doing too. Instead of just looking at 2 bits and saying how many were set there, then it can expand that to 4 bits, then it can expand that to 8 bits. Except we've got some other shifting stuff, or we've got some other masking going on in here. So it's a little bit more complicated. I'm gonna try to do the slides for this, but it's not as useful as I hope. Okay, so if this is the next set of input where we have pairs of bits representing how many bits are set on for that pair in the original, then our shift lines things up like this. And then you do the add. So now each one of these pairs in the output is going to say whether there was 1 bit, 2 bit, 3 bit, or hold on, there could be 4 bits set. 4 bits takes 3 bits to represent. You can't represent 4 in 2 bits. So that means the result of this is going to need to spill into the bits to the left of the input. So that's why in the original C expression, it masks off both pieces of input to be just the left, just the input values. It masks off just this, and then it masks off just that before adding them. Because otherwise, you might add the next column over as part of the overflow bit during that sum. Have I lost any of you? Because I lost the person that I was trying to explain this to yesterday at this part, and I really want to make this clear because it's a little important. See me later if it doesn't make sense. The next line just does the same thing again, except it shifts by 4 and it adds those results. And because you can only have up to the number 4 in each block of 4 bits, when you add them, the maximum number is going to be 8, which fits happily in 4 bits, so you don't need to worry about the overflow. So when you're done, you just mask off the result to get rid of any excess bits that were set to the left portion of that, what is now an 8-bit result, and you're clear. So if we look back at the code again, We should at this point understand up to this. And now we're hit with this. So just when we thought we were understanding things, we were lost again. But there's no reason this couldn't just continue to work, this shift add behavior couldn't continue to work for the rest of the number. So just to make sure our hypothesis is correct, let's try doing that. Let's define a mask for bytes. And I've cleverly stymied myself by calling this bytes, so let's change that back to LSBs. Okay, so our bytes are going to be zero, 8 off, 8 on, 8 off, 8 on. So we can hypothesize that you shift by 8, and then you mask to bytes, and you would get a result. And then that you do the same thing again for every 16 bits, which sounds like a short to me. The one hang up here is that we know there can be leftovers from the addition. Ooh, that needs to shift by 16. So if we run this, it's probably going to be wrong. Oh, that's correct. Okay, so we understand at some fundamental level how this is shifting everything over, how it's just taking a copy, shifting, adding. Taking a copy, shifting, adding. The only real trick then is this first one, which sets up the original 2-bit pairs that represent a real number, and once you're there, it's just addition and shifting. So the only thing we don't understand from our original at this point is what this multiplication is doing. And again, it becomes really useful to pull out some letters and try it with letters. One thing that we do know going into this is that we've just masked with quads, so we know that only the first 4 bits at the bottom of every byte have meaning. So that helps us when we go to chart it out. So we can chart out. We have what we're multiplying against and what we're feeding into it. We know that the high 4 bits of each byte don't count because we've just masked them off. We know they're 0. So now we can begin just walking through the multiplication with the letters and see what we get. Binary multiplication is pretty simple. It's just like doing decimal multiplication only with tens. We see a 1 at the very right side, we make a copy. The next thing we see is a 1 that's the 9th bit position. So that means we multiply it by everything on the first line, and we shift it over by 8 positions. It's essentially a shift. Then we see the other one. And when we get to the last one, this is the sum of this is our result. It's just like doing regular long multiplication. Once you've done every actual multiple, then we add it up. So that means in our last byte of value, we're going to have the sum of each of the quads from all the previous ones. That is to say, we're going to have in the last byte the sum of the numbers of bits that were set in each byte of input. So now this right shift makes sense, because we don't care about any of the other sums. They're wrong, and we want to get, well, they're incomplete rather, and we want to get a real, just ordinary number that we can work with. So we shift that over, and it's not alt tab correctly. And we shift it over, and we get our real final value. I barely needed exited from that slide. I'll just keep going through the slides without the sidebar, I guess. No, that's not. Okay. Why would you do this? Don't do this. We understand what this is now. That doesn't make it good. This is still illegible. You can add some comments to this. You can say, this sums every 2-bit pair. This sums the preceding 2-bit pairs into 4-bit pairs. At some point, it's not really making a difference. You can go into a really large amount of explanation, and you can still end up with a presentation like this where half the people are asleep and don't care. So the real solution is to use the x86 processor instruction, which has existed since like the Pentium 2. It's called pop count, and given a number, it tells you how many integers are in it. It's 1 clock cycle, you're done. Well, that's a little demotivating. Again, there are some applications for this sort of thing in an embedded system or a system without a full, so GCC has this built-in pop count. It created it. It's just a wrapper for the x86 assembly instruction directly. Clang copies it. The Intel GCC, not GCC, the Intel C compiler copies it. A few others copy it, or will give you some way to access it through assembly. In Java, you can do integer.bitCount. Will tell you how many bits are set in the integer. And it will also go down to this low-level pop count. But there may still be applications for something like this. Just, if you need to use this, be very, very careful. And if you can possibly avoid it, do. My concluding remarks were that something to the effect of this. You can run into this stuff. Maybe you do have an old code base that's somehow 30 years old. That's entirely possible. I knew someone who worked in the aviation industry where they had thousands upon thousands of lines that they could not touch because the testing was incomplete, or because they didn't have the time or budget to touch it, or because if it's not broken, don't fix it was the overbearing mentality. That's fine. Sometimes you get to there. Embedded code can be a pain because maybe you don't even have the option. Maybe the alternatives aren't there. And referring back to what I said about the sort of corporate culture of my friend who worked in aviation, sometimes just changing this stuff is not feasible. You have better things to do. You don't have right access to that code base no matter how much you want it. Maybe you can't change it. But wherever you can, understand it, then clean up the campground. It's going to make life better for everyone, but please don't change stuff without making sure you understand it. I think that's the end of it. If anybody has any questions, yeah.
I just have an observation. The Duff device is very clever. It's just one code.
Yeah.
As I recall, in the 60s and 70s, our main constraint was memory. We would be reluctant to squander that much code, that many bytes on that kind of optimization. We just go with that.
Sure.
Plain and simple,
Yeah.
just to see. I ran an insurance company on 32K,
Sure.
not meg. K.
Yeah, loop unraveling is a great way to waste code space. Yep. I mean, you're familiar with the reason that we have both /bin and /userbin on modern Linux systems. It's because Brian Kernighan ran out of space on their first system that they were building Unix on, and they got a second hard drive, and its mount point was user, so now they had a bin directory on both hard drives, and we're stuck with it later because of the lack of code space. Sure, that's an equal concern. Something that you point out is that Duff's device is very clever code. Don't write clever code, because then you have to read clever code. I'm not as clever reading code as I am writing code. So if I'm writing the most clever code I can possibly write, there is no way I will ever be able to read it. People are dumb. I'm dumb. It's the way it goes. Work around that when you're writing your code. Yes, I think we have a question from Brad. Joe, Brad, sorry.
Do you think there's any sort of modern practices we use today that eventually will be phased
Singletons.
out? Sorry?
Singletons.
Yeah.
There are all sorts of patterns in object-oriented design, which we use daily, which will eventually be looked on very harshly. Right now, and I can't believe I'm saying this, but JavaScript is helping the rise of a return to functional programming paradigms. We're seeing the same paradigms that people thought were the future with Lisp machines in the 70s. They weren't the future then, they might be now. Java, C++, they all have functional programming, if not mentalities, certainly trends in their design progress in newer iterations of the language. And the more functional you get, the less sense a lot of object-oriented programming methodologies makes. I think OOP is going to be considered to be something of an oops in 20 years. It's not like it's going to be gone. Java will be the new COBOL, but it's certainly going to be frowned upon. And I think we'll see that as more of an architectural thing than low-level stuff like this. But I think that's where the ending patterns of the future might be. Thanks very much to the Jodrey School of Computer Science for letting me do this. I have never given a talk in one of these settings before, and it was absolutely nerve-wracking, and you have been a fantastic audience. I'm really glad that I had the opportunity to do this, and that I was able to do something roughly from the seat of my pants enough to keep you in your seats for, I don't even have a clock because my screen resolution is too low.